Okay, let's look at the very last section of the text that we're going to cover this semester. It is on discrete time system analysis and how do we use the discrete time Fourier transform to find the output of a discrete time system. We know that we can find the output by convolving the input with the impulse response of the system, and in the discrete time Fourier transform domain, convolution becomes multiplication. So we can multiply the discrete time Fourier transform of our input sequence times the frequency response of our system. So where h of omega is equal to the discrete time Fourier transform of the impulse response of the system. For a causal system, it is also true that we can get the frequency response from the transfer function. It's our transfer function evaluated at e to the j omega. Okay. So let's use this approach now to analyze a system. We'll work an example problem. This is problem 9.4-1, where we're actually given the frequency response. It is e to the j omega plus 0.32 divided by e to the j 2 omega plus e to the j omega plus 0.16. We'll factor that denominator as it would factor as e to the j omega plus 0.2 times e to the j omega plus 0.8. If you don't see that factorization, it might be helpful to revert back to the transfer function, where since this is e to the j 2 omega and z is equivalent to e to the j omega, this term is z squared plus z plus 0.136. And of course, maybe makes it a little easier to see that this then is going to factor into z plus 0.2 and z plus 0.8, and then restoring our e to the j omega terms, we get this factorization. We're also told that the input sequence is minus 0.5 to the n u of n, so it's a decreasing sequence. It's alternating at n equal to 0 to be equal to 1. At n equal to 1, it's minus a half. At n equal to 2, it's going to be plus 0.25. We can look up the discrete time Fourier transform of this sequence in our table. It's e to the j omega over e to the j omega plus 0.5. And then now we can find the discrete time Fourier transform of the output. It's just the product of these two. So we have e to the j omega times e to the j omega plus 0.32. And then I'll have all of these denominator terms, e to the j omega plus 0.5, e to the j omega plus 0.2, and e to the j omega plus 0.8. It's actually helpful, of course we want to find do a partial fraction expansion on this. It's actually helpful here just as it was for the Z transform, to actually find the transform of y omega e to the j omega, because most of our transforms in our table have an e to the j omega in the numerator. So in this case, that cancels the e to the j omega here, and with a little work, you can show that the partial fraction expansion of y of omega over e to the j omega is 2 over e to the j omega plus 0.5, and then we'll have the e to the j omega plus 0.2 term. That corresponding coefficient is 2/3, and then finally we have the e to the j omega plus 0.8. And you can do these with by the cover-up method. For this one, for example, to find the constant corresponding to the e to the j omega plus 0.8, we cover up this term in parentheses and let e to the j omega be negative 0.8. So this would become a negative 0.3. This would become a negative 0.6. This term in the denominator then would be negative 0.8 plus 0.3. And if you carry that, go through with the arithmetic there, you'll see that the constant here is 8/3. Now we can restore the e to the j omega, multiply both sides by e to the j omega, introducing an e to the j omega term in the numerator for each of these, and then immediately following, we can then find the corresponding output sequence. It is 2 times minus 0.5 to the n. That's the inverse transform of this term, plus 2/3 minus 0.2 to the n. That's the inverse transform of this term, and then minus 8/3 minus 0.8 to the n. All of these are multiplied by u of n. And so here we've computed the output of this particular system for this input sequence.